In this video, I'm going to go over the exponential and logarithmic functions that you'll need to know for the IB Math SL exam. Starting with a few notes about what logarithms are. Helpful to see this at the beginning as an exponential equation. Let's imagine one that's filled in with numbers, so you can put it very concretely. We have 2 to the third power equals 8 is a true statement. If we were going to write that in logarithmic form, the base of the log is the same as the base from the exponential equation. So that one vocabulary word is consistent. Log base 2 of 8 equals the power that gets you from a 2 to an answer of 8. So a log should always equal an exponent, right? That gets you from the base to the argument. So you're thinking about what is that exponent that's going to get me there. So if you have to evaluate logs without a calculator, you're imagining, okay, how do I get from a base of 5 to an answer of 25 and make sure that the answer you're giving is an exponent? The exponent would be a 2. So logarithms equal exponents. They have a couple other properties of logs there. Rules of logarithms. These help us when we're trying to condense, simplify, and solve things with logs. If we have a logarithm with, let's say, base 4 of 3, plus a logarithm that's base 4 of x, and you wanted to condense these to one log, you could write that as log base 4 of 3 multiplied by x. So you're condensing it to a single log that has the same base, and the arguments get multiplied together. If there's subtraction between your two logarithms, but they're the same base, you can condense them to a log with that same base, but the arguments get divided. And this third property is if you have an exponent in your argument, that you could bring it down and write it as a coefficient, and that one works the other way as well. If you wanted to bring up the coefficient, you could write it as a power in the argument. And then this property says that the log base anything of 1 is going to be 0, because 0 is the exponent that gets you from any base to the answer of 1. We have the change of base rule there, and then 2 common log abbreviations. Log base 10, you'll never see that written because it's just written as log x with no base. And log base e. E is a number, remember, it's a very specific number, constant. You'll never see log base e of x. Instead, you'll see that written as ln of x. It has its own logarithmic notation. But I think it'll be more helpful if we practice some examples that have showed up on previous exams, so you can see logs in action. All right, so this was question 4 on an exam, 2 3-point questions. Part A is asking us just to write down the value of some logs. So evaluate logs. These are without a calculator. So remember, we're thinking about what is the exponent that gets me from that base to that argument. So the exponent that gets us from a base 3 to an argument of 27 would be 3. The exponent that gets us from a base 8 to an answer of 1/8, we basically just need to flip that 8. And so negative exponents are the things that let us flip our numbers. And the part 3 here says log base 16 of 4. I'm trying to think of the exponent that gets me from a base of 16 to an answer of 4. And those are where fractional or rational exponents come in, because you're thinking 16, I need to raise it to some power to get me 4. I know it's a square root, and we have to remember that fractional exponents serve as a different notation for rooting things, square rooting things, or if it was the 1/3 power, that would be cube rooting. And that property is going to come up again in a little bit. We have hence. There's a word that shows up as a command word in some IB questions. It means using the material that you just found in the previous part of the question. Just shrink this thing here. I want to shrink that tray, not pin it. There we go. So hence means we're going to use the previous information we just found. Log base 3 of 27 is 3. Log base 8 of 1/8 is -1. Log base 16 of 4 is 1/2. This was plus, this was minus, and we have equals log base 4 of x. So now I have an equation all filled in except for that x there at the end, and we'll be able to solve this. Let's simplify the left side of this equation. 3 plus -1 is 2. 2 minus 1/2 is 3/2. 3/2 equals log base 4 of x. And now I'm trying to think, all right, the basis for the exponent is 3/2, and I need to find the argument. You can actually write that in exponential form if it helps you to see it. So 4 to the 3/2 power equals x. The log disappears when you write it in this form. And we're thinking of the 3/2 power as a root, because the half indicates that we have a root, to the 3rd power. So the 3 actually is an exponent, but the half is a root. So we're thinking square root of 4 is 2. 2 to the third power is 8, and so x equals 8. And that's it for that example. See what else we have. Similar, we're just using our properties of logs, simplifying logs. This is question 2 off of an exam, so a pretty easy one. Without a calculator, we're imagining what's the exponent that gets us from a base 6 to a 36. It's going to be a 2. Really common mistake there would be to write 6 as the answer, thinking of multiplication instead of exponents. This next one, I can't simplify or evaluate log base 6 of 4 or log base 6 of 9 because those are not powers of 6. But what I can do is condense this first. I know that I'm allowed to condense if they have the same base by multiplying arguments together because there's addition between those logs. And once I do that, I see that I have the log base 6 of 36, which is the same as part A, so it's just 2. And then that might clue you into how you're going to approach this next part. You're going to want to condense it first, since you can't evaluate them separately. And this one is a fraction because there's subtraction between your logs. That does reduce or simplify to 1/6. And I can do log base 6 of 1/6. That's going to be -1. So just properties of logs would show up on the easier part of the exams, typically on non-calculator. So properties of functions that we need to know, logarithmic functions and exponential functions. Exponential functions have a horizontal asymptote, so they reach a floor or a ceiling. And then logarithmic functions are the inverse of those. It's like a rotation of 90 degrees. So they have a vertical asymptote, where a exponential function would have a horizontal asymptote. Let's see what we need to do with those in some questions. All right, so here we have an exponential function. This was question 5 on exam, getting a little trickier. It's an exponential function. The base is an e, which complicates this. It was on a calculator part of the test, or the calculator exam. And we're asked to sketch the graph of it. So it's important that we just acknowledge there's going to be an asymptote. It's going to be a horizontal asymptote. Even when you graph this on the calculator, it's not going to show you the asymptote. So we need to know that it's there, that there's going to be a horizontal asymptote. If you're anticipating that there's going to be one, then you might figure out where it is by looking at the graph on the calculator. So I would recommend that you graph this on the calculator. And what you'll find is that it takes this general shape like this, but the mark scheme is going to ask us to be precise in at least a few spots. So when you have to sketch graphs on exams, they're going to ask you to be precise usually at endpoints, intercepts, and any max or min points that appear on the part of the function you're supposed to sketch. And this function doesn't have endpoints. It does continue to the left forever, continues to the right forever, but they're giving us a specific interval that they want graphed, just between x values of -4 and 1 inclusive. So we should have a point on this function where x is -4 if it exists, and a point on this function where x is 1 if it exists. So if you wanted to plug in -4 to the function for x and 1, you'd be able to find out the exact values where the function is at those places. If you do that, you're going to see that it's in the 2 places I just put a blue dot. That's generally where they look to be on the graph as well, but you need to try to make them precise. And there's also an intercept in this region. It's going to cross the graph between 4 and 5, closer to the 5, and they're looking for that to be accurate as well. They don't want you to continue past that endpoint on either side because it's asking specifically for the interval -4 to 1. So this is where 3 points, and then it has to be asymptotic at 2, so not crossing this here. We've seen this happen before. People just kind of go sketchy there at the end and cross over where the horizontal asymptote would be, and they wouldn't earn full marks for that graph. Let me scroll down here and see what we have. I think there's a question underneath. Oh, good. Okay, the graph of f is translated by a vector. So this is bringing in vector translations, which is not a logarithm or exponential skill, but still something we need to know. A translation by a vector, you just have to know that vectors are horizontal and then vertical in that notation, the way they're written, that's a slide to the left or right, followed by a slide up and down. So we're not even supposed to sketch the graph of it. We're just supposed to find an expression for g of x, our new function after the translation is done. So I'm going to rewrite the function f of x down here. It was e to the x, I've already forgotten the function, plus 1, and then there's a plus 2 at the end. So if I'm shifting this graph 3 units to the right, then what I need to know is that in my function g of x, let's change the name of it here, instead of adding 3, because remember in the x you have to go the opposite direction, we're going to subtract 3 from this, and it's going to end up being a minus 2 there. And then in the y direction, the whole graph is going to shift down 1. So instead of plus 2, that's going to be plus 1. So there is my translated function, g of x. And then one more application. This is a big one from section B of the test, right? It's question 8. So it's the easier of the long questions on a calculator part of the test. We have the number of bacteria in 2 colonies increasing at the same time, and they give us a function for the bacteria in colony A. It's an exponential function, that's why it's in this video. We're asked to find some things. The initial number of bacteria in the colony. Initial is when you plug in 0 for time. So that's going to end up being A of 0. This is a 2-point question, so you might as well show a little work in case you're required to in the mark scheme to earn full credit. Well, e to the 0th power is 1, and 12 times 1 is 12. So there are 12 bacteria in the colony to begin with, right, at time 0. And very important to know that initial means time 0. Then we're asked to find the number of bacteria in colony A after 4 hours. This is a 3-point question, and we have our calculator to help us. We'll be evaluating the function at 4. In the interest of time on this video, I'm not going to evaluate that, but I think you could on a calculator. How long does it take for the number of bacteria in the colony to reach 400? So we're talking about the population equaling 400 and us trying to solve for t. So if this was a non-calculator part of the test and I had to try to solve this without a calculator, I would want to divide by 12 and then use logarithms to solve this exponential equation. But since it is a calculator part of the test, my recommendation would be to graph this as a function and graph 400 as a line. You may have to change your calculator's window to see it. But if you graph 400 as a line, horizontal line, then you can see where it crosses 400. And the x value there would be t, or time. And you'll be able to answer this question for time. And then scrolling down, we have the number of bacteria in colony B obeying this other function. And you can see this other function for B is missing a piece. It has a k where there should be a constant. But then it gives us some information. After 4 hours, there are 60 bacteria. T stands for hours, and A is the number of bacteria, or B actually in this case, because it's colony B. So it's like I have an ordered pair that I can plug in. This is really common on IB questions. If there's a missing piece, some variable component to your equation where there should be a constant, they're going to give you an XY point that you can use, or in this case, a TB point that you can use. So we'll set up 60 equals 24 e to the k times 4. E is not a variable, remember. E is a number. There's a button for it on your calculator, so you can go ahead and solve this for k. You could use nsolve to get this one solved. I think that would be your best bet. And in fact, you could have used nsolve too for this exponential equation, because exponential equations, when you're solving for the exponent, only have one solution. So nsolve is a good tool for exponential equations. And then the final 4-point question is that the number of bacteria in colony A first exceeds the number of bacteria in colony B after n hours. So we're talking about setting these two equations, two functions equal to each other, and figuring out when do they become equal and one pass the other one. So we're talking about once we know the k value, the B colony, and we would want to fill in our k value there where we would have found it, equaling the A colony. And this will be an equation with everything filled in except for t. So here you might want to graph them as two separate functions and look for where they cross. And then you'll be able to double check by looking at the graph that indeed it's colony B that's exceeding it at first, and then after some certain time t, you'll be able to see that colony A is exceeding it, or passing the number in colony B. And then we have, I don't know why they've introduced a new variable n instead of t. So in the end, instead of just saying t equals, you want to say n equals, and it'll be whatever value you find or whatever time value you find where colony A first passes colony B in size. And that's it for this one.